Okay, hello. I'm here at the Buffalo National River Water Quality Lab. I'm here with some of my friends, and they're going to talk to me a little bit about water quality and how they do their water quality monitoring here in the lab. And hello, Sean Hodges. Wave to the camera. You can smile, Sean. All right. Talk to me about what you're doing, Sean.
Today, I'm going to show you how we enumerate or count E. coli. E. coli is a better measure for human safety. So if you're going to go swimming, we want to know how safe the water is for swimming, and so we count, or we sample water for the purpose of enumerating E. coli numbers. First, we start with the vessel. It is shrink wrapped to make sure that it's sterile. It's a 100 milliliters, and that's what most regulations for water quality parameters are based on. And so we'll go out, we'll collect our water sample, like this one. We'll write where we collected the sample at. Need to know where it's collected at. It's shrink wrapped, so it's sterile. We'll take this, put it on ice in the field, bring it back to the lab. Here we'll add the media, and this is what allows the bacteria to grow. And then it also contains certain enzymes that we'll talk about a little bit later on how we can count. So I'll add this into this water. We take out a quantity tray, and this is how we quantify the number of bacteria in the sample. Again, with the sample ID, we take our sample and we pour it in our quantity tray. Make sure that we get all the air bubbles out. And now we're going to put it in this special sealer, and what this allows us to do is that this will allow us to make sure that this is not contaminated while it's incubating. So we'll send it through this tray sealer. Basically, it has a really hot roller that will seal the back to the tray. And so once it comes out...
Oh, that's pretty quick.
It's very quick. So basically now, the back is completely sealed, and the sample is ready for the incubator. So we'll put this tray into our incubator. It needs to stay in these shelves for at least 18 hours,
okay.
No more than 22 for this type of media. And it will stay in there at 35 degrees, and then we'll read them. So when they come out, they'll look like one of three things. We always take a trip blank. And so a trip blank basically enables us to know that we are not cross-contaminating the samples while we are either handling the vessels or while they're in the coolers. And so you want your trip blanks to be blank, of course. The other thing that the media will allow is that it turns total coliform colonies into yellow wells.
And so the more yellow wells, the more colonies are present in the water.
The more wells that are colored means the more of them that are in the water.
Okay.
Correct. And then, here in a minute, we're going to turn off the lights, and if E. coli is present, there's an enzyme within the media that will allow it to fluoresce under UV light. So if you want to hit the lights. So basically, this would be your trip blank. This is also important for drinking water. Your drinking water cannot contain total coliforms, and so you want all your drinking water samples to look like trip blanks. For total coliforms, there'll be yellow wells, but they will not fluoresce. And then for your E. coli, they'll be yellow and they will fluoresce. And so basically now we would count the number of wells that are positive, which are glowing, and then using a chart that they supply that will allow us to quantify the number of colonies per sample.
Okay, and why is this important again?
This is important because when you go swimming, EPA many years ago actually sampled and tested water to find out at what levels it was safe for primary contact. Primary contact is through swimming, wet wading, etc., anytime that you're in the water.
Okay,
and
fantastic.
So this is for ensuring safety when you visit the water.
Thank you. Go. Okay, thank you, Sean, very much. Now I'm talking to my friend Ashley Rodman. She also works here. I'm not even sure. What do you do?
I'm a hydrologic technician, so I help with a lot of the water quality monitoring, which includes dissolved oxygen. Dissolved oxygen is really important for aquatic organisms. Most of them need it to survive, and so we monitor it throughout the river and in tributaries. One way we do that is by using continuous dissolved oxygen hobo loggers. Not for hobos, they're too expensive, but the way that these work is we program them to record the oxygen in the water every 10 minutes, and then we place them inside of these guards to prevent rocks and other matter from breaking them. And then once they're in the guards, we hook them up to a tree root, something stable, so that they won't get washed away. And then we leave them there, and they record throughout the day, throughout the night, for however long we want. And once we decide we want to collect that data, we get the hobo logger, and we hook it up to our computer, and it will download all the data and graph it out and show us the changes in dissolved oxygen over time.
So what does that tell you?
That can give us an idea as to whether dissolved oxygen is getting too low in the river or in the tributaries, and that can give us an idea of if fish might have issues or other aquatic organisms
So
might be
essentially,
having issues.
whether fish could breathe enough and the oxygen is present. Okay, thank you very much. Okay, we're here with you at another station. Can you talk us about this one?
Yeah, so here we are at the turbidity meter. Turbidity is basically when you see a stream or a river that it's really brown, then it has a high turbidity. So there's a lot of sediment and lots of things, solids such as this, causing it to be murky. So what we do is we get our sample of water, we pour it into this vessel, we put it inside our turbidity meter, and we run a light through the sample, and it hits what's called a paddle, and the light scatters. And as the light scatters, we can get a measurement that will give us an idea of how much turbidity is in that sample. And so these are some standards or some known turbidity values, and we compare this value to these known values. So this would be a high turbidity, this would be a lower turbidity.
Okay, and how does this fit into the water quality of the river?
This is important because it can give us an idea of how much erosion might be occurring along the river or different changes to land use across the river. And turbidity can also impact aquatic organisms.
In what way?
Yes, for example, fish can have their gills clogged by too much turbidity.
And so
they
would
can
be
die.
unable to breathe. Okay, fantastic. Thank you, Ashley.
You're welcome.
I'm back with my friend Farron. Thanks, Ashley, by the way. Farron is also here in the water quality team, and he's going to talk to me about... What are you going to talk to me about?
Talking about water quality meters.
Okay, show us what you got there.
This is a multi-parameter water quality meter, and it takes several different measurements at one time, and they're all linked together with the same temperature. This is a protective cover. It's pretty fragile, so when we're actually sampling, we have a cover that goes over the top of them to keep them from being damaged. But here are the different probes that we have. Now, you've already heard about dissolved oxygen, this one here. Ashley's already told you about that one. And then we got temperature, conductivity, pH, and dissolved oxygen. And it all feeds back into a readout. We can also program these like the water quality monitors, and we can put them in the water, and then they will wake up every 15 minutes and take a measurement, and they'll keep the data, and we can download them. So we can do continuous monitoring these as well, or we can take a discrete measurement and write it down or record it into a handheld log.
By discrete measurement, you mean a one-time measurement?
One-time measurement.
Okay. Can you go back and talk a little bit about, you said pH?
Right. So we collect this when we collect the E. coli data, the fecal coliform, and turbidity. These are physical chemical parameters that relate are metadata. They go along with the dependent variables we're trying to measure in the lab, specifically E. coli. So the pH is very important in the metabolic pathway of all organisms, photosynthesis to respiration. And so the balance of the amount of hydrogen ions in the water is important to life. If the pH gets down below 4 or something along, or 5 especially, you can start to have disruptions in these metabolic pathways and the biology of the organisms shut down.
So what is a good pH range?
A good pH is 7's right in the middle.
Okay.
In the Ozarks, where we have a lot of calcium carbonate in the water, usually ranges between 7 and 8. If
Okay.
it gets down to 6, that would be a concern. If it gets over 8, not so much, but if it gets to 9 and 10, that's definitely way outside of the realm of natural.
Okay.
The pH changes as you go further down the river. In the upper river, you have the Boston Mountains, which are primarily sandstone, so your water will be slightly more acidic, maybe even less than 7. And as the base flow continues, if we walk downstream and we went, it's 132 miles, by the time we get to the mouth, or where the confluence is with the White River, you'll have a pH of around 8.
Okay.
1, 8.3, something along like that. So the geology does play a huge factor. And it also, this is the conductivity. It is the amount of ions that are dissolved in the water that carries electricity. The conductivity is related to how many dissolved solids are in the water. So your conductivity will range as you go down the river as well. The upper river coming off the sandstone primarily is going to be, after a rain, somewhere around 70 microohms. As you go further down, by the time you get to the mouth, you're looking at somewhere around 350 microohms, and that's the ability of to carry electricity across this gap in the cell.
Okay.
So that's an indirect measurement of dissolved solids.
So all of this ties in with the E. coli data and the turbidity that Ashley mentioned earlier on.
Right. We have multiple observations of the same event.
Okay.
And that way we're trying to look at multiple perspectives on changes in water quality, and that's why it's important that we always get this measurement along with any other thing that we're doing. The E. coli directly ties back to human health and during recreation, water-based recreation. That's the most important variable, but these help us determine sources. These help us determine other patterns where the E. coli is coming in, washing in from the watershed on small particulates. There are other things that are going on associated with that this will pick up. So it's multiple perspectives on the same phenomenon.
Okay, thank you very much, Farron, and thank you all of you guys. Ashley, thank you. Sean, if you're still there, thank you, and see you all later.